gives you the hard margin, like the maximum margin hyperplane. So is there anyone who doesn't see how this optimization procedure will solve SVM?
Can you quickly, I don't know, just remind me again why W is the width of the margin?
It's just because it's just because the dot product between W and X is minus B. So then if you center it, then that's like,
okay.
That's the only explanation I can think of. Basically, WX are all the points that are like the same distance from that, the distance from that line. So the soft margin problem, like the relaxed SVM, introduces some slack variables and some constraints. Is everyone okay with this? Like, does everyone understand where this came from? All right. Okay, so let's write out the dual for the original, the hard margin problem. So we're going to add some alphas as our dual variables, and we're going to multiply them by the constraint. Okay. So by setting the derivative of the Lagrangian equal to 0, and then computing, that gives you like the optimal W, which is a linear combination of the xj, like the xi's. Sorry, there should be an xi there. Now, to get that W squared term, okay, we can like compute it as the dot product with itself, which means that the squared norm of W is basically a sum over some scalar quantity, so that this alpha I, alpha j, yi, yj is a constant, and then the dot product of xi and xj. So we're going to use that later. For now, we have to know that the constraints are active for the support vectors. So I kind of made the support vectors in brighter colors there. The reason for this is, well, you've learned the Lagrangian, and yes.
How do we go from the problem to dual?
Well, you've learned how to build the Lagrangian, right? So when you've got a primal problem, like so can I just use one of the, which one should I use for writing? I guess I'll use that one for writing. Okay, maybe not. All right. del of x alpha as, let's say we've got several times. We're going to build it as f of x plus lambda or alpha I, because we have okay? So this is how we build the Lagrange, which gives us the dual optimization problem.
Oh, the dual is like a Lagrange multiplier.
Well, the dual problem is the thing that gets you the correct alphas. Okay, so when you do the optimization, if you want to minimize over x and maximize over alpha. Oh, this. Okay, so the alpha maximization problem, that's the dual problem. If the alphas are the dual variables, and the problem, the convex I guess the program that gives you those the values for the alphas is the dual problem.
So what is a dual space? And
Sorry?
So what is a dual space? And is there
The dual space are the values that alphas contain.
So is there always a dual form or a prime form?
Yeah, for convex optimization. I mean, for constraint convex optimization, yeah, there is. I mean, for unconstrained, there also is. It's just that it's redundant.
So the prime form is always one form corresponding to the
Yeah. Yeah, so, I mean, I guess Alex didn't get a lot into this, but there's something called the duality gap, which tells you how different the solution for the dual problem is from the solution to the primal problem. So there's sometimes you can't really get the dual problem, you can't really solve it and get a close enough answer to the optimal answer for the primal problem. Okay? All right. So, well, okay, so let's, I mean, in this case, f is just the w squared, right? And the constraints are what's on the side of x, right? So we just apply the formula and we got the solution. Okay? Now, so we took the derivative of the Lagrange with respect to w, and we got that if we knew what the dual variables were, we could compute w as a linear combination of them. Okay? Good. Now, again, so the square norm of w is the dot product of w with itself. So we can compute that and write it as a function of alphas and y's. Okay. All right, and as I said, the constraints, does everyone understand why the constraints are only active for the support vectors? Okay, so what does it mean that the constraint is active? It means that those alpha k's are greater than 0. Okay? And that only happens for the points that are exactly on those lines that I drew there. Okay, so you have two hyperplanes. This is the hyperplane with function. So let me write it. So you have the same equals -1. So these are the two hyperplanes that I need. Okay. So the support vectors are exactly on the hyperplanes. So basically this part of the dual will be 0 for them. Okay. And then the alpha alpha i's will be something positive. Okay, so one of those things is 0. Either the alpha i's are 0 or this. Okay? For the support vectors, the alpha i's are not 0. Okay? Alright. So, moving on, let's rewrite the dual as, let's write the dual optimization problem. So we're maximizing over alpha, okay? And we used this formula to put it in the W squared. And then we'll have plus alpha I here. Okay. And we know that, so the constraint is the sum over I of alpha I, yi is 0. Okay, that's just the constraint field. Now, we're going to solve this dual optimization problem, which is something you've done in the homework. And we're going to get alpha I. So who's done the SVM, like the SVM problem? Okay, so since everyone's done it, you guys should be aware that, okay, you do it, you solve alpha I, and then you can get W as the linear combination of it. So the SVM for the soft margin is pretty much the same as the one for the hard margin, except we are going to cap the value of alpha I at a constant C. So we won't allow the dual variables to go past a certain threshold. So this kind of concludes SVM. So basically, if we were just interested in building a linear classifier, we'd be done now. But the problem is we might want some nonlinear classifier because the data is not necessarily linearly separable. So we'll apply a transformation to a high-dimensional space where the data is linearly separable. And we're going to call this the mapping, the feature mapping. So the x's are the inputs, and we're going to generate a map of features that we are going to run SVM on. So instead of running it on x's, we're just going to replace that with w's, with phi's. Okay. So the phi gives you the feature map. Well, the problem here is that okay, so you've obtained a linear separator in this really high-dimensional space. The dimensionality of phi of x is a lot larger than that of x. You can talk like billions of things, okay? So phi of x is really expensive to compute. So you don't want to do that. Okay. But what we notice is that the dual formulation no longer depends on W. It only depends on the dot product. Okay? So it only depends on phi of xi, phi of xj. So we don't really have to compute phi of x for the purposes of the optimization problem. What we need is just the dot product, and we're going to call that the kernel function. Okay? So it's basically a two-variable function, which can be written as a dot product. So far, let's call that our definition of a kernel. Okay. Now, we've put it in there, and there's a closed form for it. So our entire optimization problem changes to this. Okay, which is perfectly, solvable. It's kind of inefficient because you have to compute all the. It's n squared, right, in the number of points. You have to compute all the, dot products, like all the cross terms. Okay, but basically this is the kernel trick. You never compute the actual feature map. Like you have a really large feature map, but because you have a closed form for that dot product, you don't really need to compute it. You just learn using the closed form K. And this gives you like a constant time for high dimensional dot products. Okay, you do all Okay, so so far any questions? Yeah.
So can you explain how the kernel is a closed form of phi xi and xi?
Oh, so for that you come up with specific kernels that you know can be written as a dot product, or you compute them. Like I guess you had, or maybe you didn't have some examples in the homework, but you can write a very large dimensional. There are some formulas with which you can reduce the dimensionality of that. So you just write it out explicitly, like you get like a Fourier series or something, and you get like a closed form for that, right? So for a polynomial, let's say you wanted like an exponential thing, right? Like let's say you wanted this feature map, 1 plus x squared plus so on, right? And then you had the inner product of this. You just compute the inner product of this, and you try to like, write it up as a closed form thing. Okay, that's just this. So you do the math before you actually do the math. I'm not sure that for this thing there exists such a thing, but in many cases you can find tricks that kind of allow you to do that. Okay, so just like mathematical like computations. Okay. But you know what the closed form solution is before you run the optimization. Okay, is that okay? Everyone finds it okay. All right, so what about a runtime? Like, what happens when we need to classify some point at 0? Okay, so remember, W actually depends on alpha. Right? Okay, and B can be obtained from W and alpha. Okay, but our classifier uses W. Okay, so do we have a problem? Okay, well, as it turns out, we don't really, because we don't really need W when we've got dot product. Okay, we can write that dot product between W and phi of x, or phi of x0, as a sum, right? We just use the properties of the dot product, and we obtain formulas for both, the dot product between W and phi of x0 and B. Okay, so let's recap kernelizing. Yeah.
So can you go back to the first slide? So B is also a vector.
B is B?
Yeah.
Yes, B is also a vector. No, sorry, no, B is a scalar.
B is scalar?
Yeah.
So
sorry.
when you calculate.
Yeah, so the same thing, right? So B is yk minus W, so let me write it down. You guys see any eraser? Oh, there. I'm not sure if this erased so much. So you can write E is like 1 minus dot W.
For each support vector, we should have.
Sorry?
For each support vector, we should have a B.
No, not really. We average those out. Like there's the same B, right? That thing, so B should be equal to, like, among support vectors. Okay? We can compute B using any of the support vectors. Okay. So we're just going to use the formula for W, which is like the sum of xi. Okay, so it's alpha I, 4I, and 5. Okay? Okay, dot product with phi of x thing. Okay, and now we just, we can take the sum out of this dot product, right? And also the alpha I and yi. what we'll do, so recap for kernel SVM. We're going to pick a kernel. We're going to solve the dual optimization problem to get alpha. So we're not computing any explicit feature maps for this. We're just computing the closed form value of the kernel. And then we'll compute v using the support vectors. Okay, and finally we'll classify, taking the sign of a weighted average of the kernel of the point we want to classify and all the points that we have in our data set. Okay. All right, everyone. All right. So that's kernel SVM. So there are of course other uses of kernels. So there's logistic regression with kernels. Multiple kernel boosting. Alex has a paper on trees and kernels. The first paper I think is by Trevor Hasty. That's a really good paper. And conditional mean embeddings, which kind of provide a local model for a local conditional model. Okay. Okay, so more on kernels. I've been asked what the gram matrices. So for a set of vectors in the inner product space defined by the kernel, the gram matrix is basically just the kernel evaluated at pairs of vectors. Okay. For the reproducing kernels, so let's say we have a Hilbert space of functions, and for that space, we'll have for every function in that space and for every point, we'll have a point evaluation function, so it's defined as I wrote there. So think of when you have a Hilbert space of functions, you have to consider the cross product between the function itself and the point specific k of x to get the value of f at point x. Didn't Layla go over Hilbert spaces in the recitation? Okay, so it's okay. So a Hilbert space is just so you've got like a space of stuff over which you have defined the inner product.
But how is that a function? Like that would
So you can define the inner product between two functions in some way. Okay. Okay, like you can define it as an integral of f of x1 times f of x2. It just needs to satisfy certain properties.
Oh.
Okay, and sorry?
What did kx
Kx is just, so it's, Kx is the point evaluation function. So I have for every point x in my set, I have this function that I need to get such that whatever other f, if I get the, okay, so let me explain it. So I have a point x, okay, I map it to kx. So for every function f in my Hilbert space, when I need to compute f of x, right, I just compute the product of f with k of x, and this gives me f of x. Okay, it's a fast way of computing, of evaluating the function f at point x using just the dot product. I don't know if it's necessarily fast. That's fine. It's a different way of thinking of how to evaluate a point at a function. Okay. Does everyone sort of follow? Okay. So the reproducing property is just says that basically k of xi is the complex conjugate of k of yx. Okay, which results from the definition of the kernel. Okay. Does everyone see how that kind of makes sense? The reproducing property? Okay. Yes.
kx a function?
So yeah, kx is a function, right? That's why I can compute the, the dot product between kx and f, because they're both functions in that complex space. Okay? All right. So let's try to solve this SVM problem. So what's the maximum number of support vectors for a linear classification problem? Or better yet, what's the maximum number of useful support vectors for a linear classification problem? So this is related to something you've recently studied. And for the 1D case, we can see that we have like two possible, support vectors. Now, for the 2D case, we have like three, like useful support vectors. Okay, what do you think is the concept? What concept does this relate to? Yeah, so it relates to the BC dimension of the classifier, and it's because we can't really have that case to be the support vectors in 2D, right? We'll need to have enough. The support vectors need the number of support vectors, like it needs to be a set that we can shadow. Otherwise, we can't classify them. Okay. All right, and now a question for kernel SVM. So you have here the result of training different kernels on some data set. So we have a linear kernel, a quadratic polynomial kernel. So let me write I forgot to write the quadratic polynomial kernel. So it's x transpose y minus. Okay. So, and then the RBF kernel. Okay, so what happens when we translate the points up by a large constant on the vertical axis? What do you guys think happens with a linear kernel? So you're using the same, training procedure, right? But the points are shifted up on the y-axis, and they stay the same on the x-axis. Okay, would anyone like to try that? Sorry?
Nothing
Okay.
happened?
Stuff actually does happen with the linear kernel. Not all of them, but
If you translate all the points up?
yeah. Well, you translate all the points up, right? But you've moved them away from the origin, right?
Right.
So assume that corner is your origin. If you shift them upward.
Oh, okay, yeah. So the bias changes the view.
Yeah. So it's gonna change. Well, let's see how. So basically, for the linear kernel, it's shifted by 10 units. Okay? All right. For the quadratic polynomial, because the y values are going to influence the kernel a lot more than the x values now, because they're going to be larger, the bound will be more curved. It will be more arched upward than it already is. Like it will be narrower. Okay, now the bound basically for the last one, the bound retains its relative position. Okay? Yeah.
Won't the B value change on the same version? And won't it just stay the same or?
I mean, so I don't know how to. Yeah, the B value will shift, right? But I mean, the question isn't how the B value will change; it's how the kernel itself will change, like how the separation boundary.
Yeah, but I thought if the B value changed, then essentially it
Yeah,
stays
like-
the same shape and just.
Yes, so that's what happens for the linear and RBF. So the boundary doesn't stay the same; it shifts up a little bit. Okay. So what you said was kind of right. Like if we were to look at it, it would be the same, but it does. I mean, it needs to shift, right? Okay.
But it doesn't come to the quadratic polynomial, it doesn't give exactly one.
For the quadratic polynomial, because the y's are so big, they kind of drag the boundary upwards. Okay.
So what is the RBF? Those stay the same?
Because the So the value of the kernel is basically the same for each pair. So by shifting the points upward, I have to.
Every two points are the same.
No, it means just that when you compute k of xi, so it means that when you compute k of x, y plus b, you get the same value as k of x, y. Okay. If this is true, then nothing changes. So in the midterm, you might have something like, we're going to apply some transformation to either x or y or both, and ask you how the boundary changes. Like that's an example of things. Okay. All right. Okay, so actually that's all I had for this week. The midterm is on Monday, so you should feel free to search for questions from previous years. I might be able to provide, like, they're all online. They should all be